So welcome back friends to another lecture on quantum field theory and quantum entanglement. In the previous lecture we have been looking at the S matrix. I defined what an S matrix is and what are in and out states. Essentially we defined in and out states as the states which are coming from minus t is equal to minus infinity, in and out in states to be essentially the eigenstates of the H0 Hamiltonian in the interaction picture, and they are assumed to be coming from t to minus infinity. And then there are the out states which are coming from, which are defined in the limit t tends to plus infinity as the eigenstates of the H0 Hamiltonian in the interaction picture. So but then there is a unitary evolution operator which takes the in states to the out states, and that matrix which takes from the in states to out states, which is unitary, which is called as the S matrix essentially. Now we can re-express this in terms of u t t0 essentially at the and we have seen that the u t0 is expressed in terms of the Dyson series, and the S matrix is nothing but just a unitary matrix which is called also the scattering matrix. At the leading order we looked at an example of an meson decay. Okay. So in which what we have done is we have taken an S matrix in which the in states just are mesons, and then the final states are just say nucleons. Essentially we just used the psi dagger psi phi as the L interaction. Okay, this is okay, we have not defined what the Dirac fields are as of now, but I just assume that Dirac fields are exactly the same degrees of freedom as a complex scalar field essentially. So that's the basic idea I had done, and so I have put in two creation and annihilation operators associated with each of them essentially. That's the assumption I made, and this is your S matrix which is unitary. And what we have seen is that if I just take the plane wave part and I put it on the in this picture, I end up having one has delta power 4 so this is P if the P meson essentially, let's say call it some meson, so me M minus Q nucleon minus R nucleon. So so you will end up having a relation which is essentially tells you that energy momentum conservation of the four momentum vectors associated with the meson and the two nucleons essentially. So this is the nucleon Q and R are the nucleon momenta, and PM is the meson momenta. So this we showed it last time. It's simple that you just take the plane wave part and plane wave part associated with each creation operator. Essentially you have the creation operator. When you write the fields in terms of the creation and annihilation operators, you take the creation operator and it comes associated with the plane wave part, and that is being pulled out essentially, and then it gives you this particular relation essentially. Very good. Now let's go further essentially. Let's go further and looking at various aspects about this what do you call actually the S matrix essentially. So the one of the main things is that we want to compute the scattering elements using the full Dyson formula or the Dyson series. So that means what it means is that you write down, okay, so so if I want to compute f t time order product hi of x1 hi of xn I. Okay, so this is your S matrix element, essentially SFI. So we want to compute, say, beyond the leading order. So we want to put in insertions of the interaction Hamiltonian, okay, where I and F again, okay, into the for the in and out states, as again these are your free states essentially. So we eigenstates of H0. So I and F, both of them are eigenstates of X0, but Hi is in the interaction picture essentially. So now what would be easier essentially, that since Hi contains creation and both annihilation operators, if we can move all the annihilation operators to the right, okay, if you move all the initial, okay, so they will start annihilating all the i's essentially. That's the basic essentially. Now the point is that we have to somehow Hi's, let me call there okay, contain both now. How did we see it last time? Essentially we saw it by saying that Hi examples, everything, I think it's easier understood if you have as many examples as possible, if we can construct as many examples. So for example, we had lambda phi 4 theory, in which we had phi of x1, phi of x1, phi of x, phi of x. So for a complex field we'll put two of them to be starred essentially, okay. And we had done the quantization of the complex scalar field, and then this will have something like, okay, let's start with a plus b dagger. This will dagger a plus b. So this will be a plus b dagger, and this will be a dagger plus b. So this product, the H interaction, which comes with some lambda coupling constant, essentially this constant is called a coupling constant, okay, will come with both creation and annihilation operators. Now what we always need, if you remember in that when we started writing in the previous lectures, that it is always useful because we want the vacuum to be normal ordered, right? Essentially at the end of the day what we want is the vacuum to be normal ordered. So what it means, that can be done by pushing all the annihilation operators to the right, okay. We don't want some vacuum to be the vacuum of this states, essentially of this state should be non-zero, okay. We want to set it to 0 essentially, that's the point. So we don't want some something. So it makes our life easier. So we would prefer, as we have seen before, we would like to have the vacuum of these states essentially to be normal ordered essentially. What it means is that this means, all annihilation operators are to be pushed to the right. So this is a basic idea that, okay, now here we have an issue. Okay, now here we have an issue. The point is that we know that if you interpret this entire thing in terms of A and B dagger operators, in terms of these harmonic oscillators, you will need to do normal ordering, so that you need a vacuum which is well defined and everything. But at the same time, when you try to expand everything in terms of the Dyson series, you need time ordering of the operators, because HI are in the interaction picture. They need to be time ordered essentially. Okay, they need to be time ordered. This we have seen, because this will lead to inconsistencies essentially if they are not time ordered. So how do we go from time ordering to normal ordering of this? So what is the relation between this time ordering and normal ordering? This is really given by a wonderful theorem called Wick's theorem. So before going that, essentially let's try to recover something called the propagator. So what is to define the propagator? Let's write phi of x okay, where pi plus of x So what it takes out is the annihilation operator with positive wave functions essentially. So pi minus of x so I just wrote the annihilation creation operators separately essentially. With and the creation operators with negative wave functions essentially. That's plane waves, negative plane waves essentially, negative energy plane waves. Now this pi plus and pi minus really doesn't make sense, because you have pi plus dagger is equal to pi minus, and okay, but anyway. So pi plus has positive frequency, positive energy states, and pi minus has negative energy states. Okay, anyway, now let's choose x0 greater than y0. x0 means it's a time component of x4 vector, and y0 is the time component of the y4 vector essentially. This I think it's self evident that let's choose x0 is equal to x0 y0. Then let's calculate the time order product of t pi of x pi of y. So that is pi x pi y, that is equal to pi plus of x plus pi minus of y. Oh, okay, I made a mistake here. Times pi plus of y plus pi minus of y. Now you can expand this. This will give you 4 terms: pi plus of x, pi plus of y, pi minus of, so the cross terms and everything essentially. So this you can express this as okay, let me write it down as pi plus of x, pi plus of y plus pi minus of x, pi plus of y, pi minus of y pi plus of x plus pi plus of x pi minus of y plus pi minus of x pi minus of y. So I have these 4 terms. Then I added and subtracted this, meaning I am adding. So you have these terms pi minus of x multiplying pi plus of y and pi minus of y multiplying pi plus of x. But then I added this commutator, which essentially is pi plus of x pi minus of y minus pi minus. So you are adding and subtracting. Essentially the basic idea is that you are adding and subtracting. Now the basic thing, okay, the basic thing here, the reason I put it up in this particular fraction essentially is that now the basic idea is that if I normal order this, because I want to put everything on the right, all the annihilation operators on the right. So all the annihilation operators are contained in pi plus. So pi plus should be always in the right. So you have pi plus, and except for the pi minus, okay, doesn't contain any annihilation operator. But once you normal ioderize it, it doesn't have anything. So you leave it as it this thing. But when you do this, because you added this pi plus on the right, you pick up this particular term in this fashion. So the time ordered pi plus pi minus is equal to time order product pi x pi y plus, what is this term? This is nothing but dx minus y. I will come to what this term is. This term is nothing but the propagator. Okay, well, this is part of the propagator. Now if you do the same thing, okay, so the point is that the time order product of pi x pi y is a normal order product of pi x pi y. On pi minus pi y there is no annihilation operators, so we can forget it essentially, and we can forget normal ordering. Okay, so whereas is equal to normal order product, normal ordered product. So that means this is all normal ordered plus this d function which is of xy. I will come to the d function in second. Essentially now what we can do, you can try to do t of, instead of pi x pi y, I will do the opposite, pi y pi x, and this will give me normal order product of pi y pi x plus d y minus x. Okay, this gives me normal order time order product of pi y pi x gives me normal order of pi y pi x. Okay, now this essentially is this. Normal product of pi x pi y plus d of y of minus x. So this putting together, this is equivalent. The normal order product is the same, essentially same. Okay, see this pi plus pi minus, the way we have written it, if you take pi y and pi x also, when the moment you put in normal order, it will be the same thing, because you always want pi plus on the right hand side. So this is obvious. Okay, see, this is obvious, this will be the same as the above. So finally what we have is time order product of pi x pi y is equal to normal order product of pi x pi y plus delta f x minus y. So this is the relation between, oh sorry I missed this too. So this is time order product and normal order product. Okay, let me just put you back into the picture that we want to see the time evolution of a state in the interaction picture, and we did the time evolution in terms of a unitary operator, okay, which is dependent only on hi, the interaction Hamiltonian, and then we showed that this expansion, meaning this expansion can be written in terms of a time ordered product in hi, so that you don't violate causalities and so on. So this has to be, and finally when you are writing it in terms of the S matrix, essentially what we are, or independent of the S matrix right now, essentially we see that this time order product E is equivalent to normal order product plus propagators, or in other words we will say these are contractions essentially. Okay, so now let me define the propagators. Okay, so the propagators are nothing but so you take your phi of x essentially. Okay, now let's write your pi in terms of the creation and annihilation operators essentially. Let me just write it down. Okay, phi of xt is equal to what we defined is d cube of p 2 pi by cube 1 by root 2 ep ap e power minus ip of x. Okay, ap dagger, I think this is the same thing which we minus I plus I p of x. Okay, this is the same thing which we have written here essentially, this one pi plus and pi minus. So when we write this down essentially we were looking at equal time commutation relations and everything essentially. Now what about an expression which does the calculation of I'll say so if you want to probe the causal structure of the theory, okay, now what is the amplitude to find it at a different point essentially the okay, so what we want is, so if we have a particle okay at a space time point x, say for example, okay, phi of x, what is the amplitude to find it, or if it's okay, let's start it with pi of y, what is the amplitude that you will find it at a space time point y x essentially, okay, at a space time point x essentially. So how is this given? This is given by a function, or the amplitude is given by a vacuum expectation value of phi of x pi of y essentially. This is given by integral. Now we know what is pi of x pi of y. I'll explain this more essentially why this is required. 2 pi by 6 because 2 pi cube 1 by root 2 ep prime 0 ap dagger 0 and the plane wave part e power ipx plus e power I prime y. So this function, now here you can calculate this essentially, this function, okay, this you have this is p prime, a dagger p prime, you can use the commutation relations and this will end up being d cube p 2 pi by cube 1 by 2 ep, okay, and then e power I minus ip x minus y, and this function is called dx minus y. Okay, okay, this function is called px minus y. So what is this? This is essentially a way of probing the causality. The point essentially is that you cannot have a particle at a point y, say for example reaching at a particle x, reaching at its amplitude should not reach x such that it should pass through the light cone. Essentially it should pass through the light cone, it should not pass beyond the light cone. Essentially it should not pass the beyond. The basic idea is that it should conserve the causality. That means it should not travel, the amplitude should vanish if it's beyond the light cone essentially. So it should satisfy this light cone, which essentially conserves the speed of light. So you cannot have amplitudes cancelling, meaning you cannot have amplitudes which are large beyond the speed of light essentially. This function, what is the nature of this function? The point is that how did we calculate it? We just expanded pi and in terms of these functions we put it back into this in terms of this particular thing. Use the commutation relations, I didn't do the full thing, and then you ended up having this function essentially. Okay, so now this is the first step of finding a propagator. Okay, and okay, and then I'll stop here, and in the next class I'll continue with the propagators. Okay, so and we already saw the Wick's theorem here. This is nothing but the Wick's theorem, but I'll formally do it in the next class essentially. Okay, I'll formally do it in the next class. So we are already actually reaching the did the propagators, and these propagators will vanish outside the light cone, where they actually decay exponentially outside the light cone, and we will see other further properties of it in the next class essentially. So let me stop here. We'll continue dealing with propagators in the next class, and I hope to see you soon actually. Thank you very much.